This question is asking, what intermolecular forces are present between ethanol and methanol? Okay, so with that being said, give me a few seconds to make sure that we get any sounds. Ethanol and methanol, right? Let me just write the question down. Intermolecular forces present between ethanol and methanol. So another example of things that you unfortunately have to memorize, but let's actually break this down by their prefix. So let's start with methanol, which is actually the prefix of methane. So methane is CH4, okay, because that is one carbon in that hydrogen group, because these are hydrocarbons that I'm listing out. And methanol is when you have an hydroxide group added and you replace it with one of the hydrogens. So you have CH3OH, okay, which kind of look like this if it was drawn out, okay, because that carbon bond is there. Ethane, okay, is now two carbons, so now you have C2H8, I believe, yeah, well, C2H6, that should be better, yeah, times 2 plus 2, there we go, C2H6, and now same process of ethanol, you would replace that with a hydroxide group, so you have C2H5OH, and you kind of look like this. Let me do that better. Okay, so that's methanol and ethanol. Okay, and now they're asking for the intermolecular forces present between ethanol and methanol. So what are the list of intermolecular forces that are possible? We have the London dispersion force, okay, which is present in everything. We have, if I remember correctly, polar or dipole, there we go, pole bonds. We also have hydrogen bonds, and we have ionic bonds as the last one. So, well, ionic forces in a sense. This would be how it goes from weakest to strongest. Okay? So, with that being said, we'll actually go through and list out what we do have, okay? So, between methane and methanol and ethanol, think of these two floating near each other and everything. So, with that being said, we're going to highlight them. So, London dispersion, as I said, every single type of molecules have this force that attract each other. It is the weakest force. It's kind of like a gravitational field, very weak, to where molecules that are floating around, they'll like to attract each other just slightly. So that is a check for that. That definitely has that. Dipole. For this one, you kind of have to look closer into your intermolecular force, like the bonds there. And you can actually see here, right, for the dipole, you have a carbon attached to an oxygen. Same thing here, carbon attached to an oxygen. So the way you figure out dipole is by looking at the periodic table, the electronegativity, draw in a different color, the electronegativity, and seeing if your molecule is polar, has a polar and a polar, has a positive and negative pseudo charge, okay? So if you compare carbon and oxygen, so the cutoff for polarity is 0.4 difference of electronegativity. Oxygen is 3.44, carbon is 2.55, so 3.44 minus 2.55, we have 0.89 difference. So with that being said, actually, this is going to have a positive, positive, I guess, polarity, and this is going to have a negative on the oxygen. Same with here, positive and negative, okay? So with that being said, if methanol and ethanol were floating, like a bunch of methanol, ethanol, you'll typically see the carbon be attracted to the oxygen, okay, because that's kind of like their that's how they will be structured, because the carbon will serve as kind of like the positive polar end, and the oxygen will serve as a negative polar end. So with that being said, it does have dipole-dipole bonds as well, so you can check that off. And now hydrogen bonds. You're probably wondering why I skipped over the oxygen and the hydrogen, because that could technically count as polarity, but this is actually one of the hydrogen bonds. Okay, there's 3 types between hydrogen and oxygen, as here. Hydrogen and nitrogen, that's another hydrogen bond. And hydrogen and fluorine, okay, NOF is usually the acronyms they use. So because we actually have hydrogen bonds as well, when methanol and ethanol float near each other, you typically see the oxygen of one try to bond the oxygen one try to bond the hydrogen of the other, as it kind of form that weird in a sense hydrogen bond. You see this OH here, so this O, we kind of want to attack that H, okay, because that's just typically how oxygen or any other of the 3 I mentioned, nitrogen and fluorine, like to roll, is that when they're in the presence of hydrogens, they just like to grab. And then you'll see as this one's trying to grab that, maybe another ethanol molecule is trying to grab their hydrogen, so you have a lot of that hydrogen bond interaction there as well, okay? So with that being said, this is what we have so far. Ionic specifically says between a metal and a non-metal. When I've written down the names for methanol and ethanol, do you see any metals in there? Unfortunately, no. We have hydrogen, which is a non-metal, carbon, a non-metal, and oxygen, also a non-metal. So it does not have ionic bonds. So the 3 forces you'll see there are London dispersion, dipole-dipole, and hydrogen bonds between ethanol and methanol, okay? And typically, maybe not always the case, but typically if you have a hydrogen bond, you most likely have dipole-dipole, because whatever the oxygen is attached to is on the other end, or nitrogen or fluorine, they're forming that dipole disparity, where one side is a little bit more positive and the other side is more negative. So we have the pictures correct for ethanol and methanol, so that's good. They talk about the van der Waals forces, which is the London dispersion, okay? And the other one is hydrogen bonding, which is more dominant than the first one. And unfortunately did not mention there is also dipole, and it's important to make the distinction, because for questions like these, typically if you miss one part, you still miss the whole question, because that is dipole still play a very important role in terms of the orientation of the methanol and ethanol in the solution as well. Because just because the hydrogen bond is stronger and they prefer that, you have to consider, like, the spacing and whether they can actually fit there, like stereochemically, which is the shape and everything. So all these things do play an effect as well. So that would mean this is unfortunately incorrect. And yeah, so